Public Exam Review for Advanced Math 3200, Unit 5, Chapter 5 on Trigonometric Functions and Graphs. This presentation will conclude Solving Trigonometric Equations Algebraically, Part 2, where our solutions will be represented as general solutions. Here we will focus on algebraically solving trigonometric equations using general solutions. Here are a few tips that we can use to solve trigonometric equations. First, we can isolate the part containing the sine or cosine of an angle to the left side of the equation. If the terms on the right side of the equation equal a -1, 0, or 1, then we can use quadrantal angles around the unit circle to determine the solution. If the terms on the right side of the equation equal plus or minus a half, plus or minus √3/2, or plus or minus √2/2, then we can use special angles around the unit circle to determine the solution. If the terms on the right side of the equation are not one of the above, then we would have to use a calculator to determine the solution. Always sketch a diagram to indicate which quadrants the angle may be found in, and always determine the reference angle given by theta subscript r. For general solutions, we add 360 degrees times n, or 2 pi n radians, where n belongs to the set of integers. This indicates the number of revolutions to make in either a positive or negative direction that will give us all the solutions that satisfy this equation. In example 1, which represents the zeros of y equals cosine of 2/3 x. Here we are asked for the zeros of the function. In order to determine the zeros, we have to let y equal 0. So therefore we have the cosine of 2/3 x is equal to 0. Note that the right side of the equation is equal to 0, so we will use quadrantal angles to determine the solution. Here we can let theta equal 2/3 x and replace 2/3 x in our equation with theta, so that now we have an equation that we recognize. To sketch a diagram of what is happening here, we can sketch in our unit circle, and for these quadrantal angles, the cosine is equal to 0 at pi/2 radians. The cosine is also equal to 0 at 3 pi/2 radians. So the first angle theta, theta1, can equal pi/2 radians. If we want to get back there again at that terminal arm, we can add multiples of 2 pi n. In the second case, theta2 can be given by 3 pi/2 plus 2 pi n as well. So what that means really is that at pi/2, if we add 2 pi radians, we get back there again. Or if we subtract 2 pi radians, we have the same terminal arm as that of pi/2 radians. Similarly, for 3 pi/2, if we add 2 pi radians or multiples of that, we get the same terminal arm. If we subtract 2 pi radians, we're back there again. Both of these statements can be combined into one. Notice that if we are at pi/2 radians, all we have to add is pi radians to get to 3 pi/2. So both of these statements can be combined to give us theta is equal to pi/2 radians plus pi n. All we have to do there is add multiples of pi radians. So if at pi/2 we add pi, we get to 3 pi/2. Add pi, we're back here again. Add another pi, we're back at 3 pi/2. So then we can replace theta with 2/3 x is equal to pi/2 plus pi n. In order to solve for x, we will multiply both sides of the equation by 3 over 2. So then we are left with x is equal to 3 pi over 4 plus 3 pi over 2n, where n belongs to the set of integers. And that gives us all the solutions for this equation. So that answer then corresponds with C as the multiple choice item. In the next example, we are asked to solve for all possible x, where cosine x is equal to cosine of 3x is equal to 1/2. In order to determine this solution, let's let theta equal 3x. So then we have the cosine of theta is equal to 1/2, and that is an equation that we recognize from Chapter 4. Note that cosine is positive in quadrants 1 and 4. So this time we can use special angles around the unit circle to determine our solution. We can put the terminal arm of one angle in quadrant 1 where cosine is positive, and cosine is also positive in quadrant 4. So cosine is 1/2, so the sine must be √3 over 2, and the related reference angle here would equal 60 degrees, which is the same as pi over 3 radians, since all multiple choice answers are in radian measure. In quadrant 4, cosine is 1/2, but the sine would be a negative √3 over 2 with the same related reference angle. So to determine our solutions then, in quadrant 1, theta is going to equal pi over 3 radians. We add multiples of 2 pi n to get back there again, where n is a member of the set of integers. Replacing theta with 3x, we have 3x is equal to pi over 3 plus 2 pi n. In order to solve for x, we multiply both sides of the equation by 1/3. X then is equal to pi over 9 plus 2 pi over 3n, where n belongs to the set of integers. That represents one solution for this equation. As well, in quadrant 4, theta, the second value for theta, would equal, that's going to be 2 pi radians minus pi over 3, and we still have to add 2 pi n, where n belongs to the set of integers. So 2 pi minus pi over 3 is equal to 5 pi over 3 plus 2 pi n. We'll replace theta with 3x. So we have 3x is equal to 5 pi over 3 plus 2 pi n. Then we have to multiply both sides of our equation by 1/3 to solve for x, where x is equal to 5 pi over 9 plus 2 pi over 3n, where n is a member of the set of integers. So this represents another solution for this equation, which corresponds with A as the multiple choice answer. In example 3, we again are asked to solve for x, where 4 times the sine of pi over 3x plus 23 is equal to 25. X belongs to the set of real numbers, which indicates that we are looking for the general solution, or for all possible values of x that satisfy this equation. So the first thing we need to do is to isolate the sine of the angle for which we are looking for. So we have 4 times the sine of pi over 3x equals 25 minus 23. So we'll bring the 23 to the right-hand side. Then you've got 4 times the sine of pi over 3x is equal to 2. Dividing both sides by 4, we have the sine of pi over 3x equals 2 over 4, which is equal to a half. Now we will let theta equal pi over 3x, and we have the sine of theta is equal to 1/2, which is another equation that we recognize. Notice that sine is positive in quadrants 1 and 2. So to sketch a diagram of what's happening here, we can draw our unit circle, putting the terminal arm of an angle in quadrant 1, and another angle will have its terminal arm in quadrant 2. If the sine is equal to 1/2, the cosine must be √3 over 2 in quadrant 1, and the related reference angle in radian measure would equal pi over 6 radians, which is equal to 30 degrees. In quadrant 2, we would have a negative √3 over 2 as the value for cosine, and the sine is still a positive 1/2. So now, in quadrant 1, the first angle theta will equal pi over 6 radians. We add multiples of 2 pi to get back there again. 2 pi n, where n belongs to the set of integers. We have to replace theta with pi over 3x is equal to pi over 6 plus 2 pi n. In order to solve for x, we multiply both sides of the equation by 3 over pi. So on the left side, 3 over pi times pi over 3x just leaves us with x is equal to. On the right side, the pi's will cancel. 3 over 6 is just equal to a half, plus the pi's will cancel, and 3 times 2 will leave us with 6n, where n belongs to the set of integers. This represents one solution for this equation. Similarly, in quadrant 2, we can determine the second value for theta to equal, that's the same as pi minus the related reference angle, pi over 6. And then we still have to add multiples of 2 pi n, where n belongs to the set of integers. So we have theta 2 would equal, pi is the same as 6 pi over 6 minus pi over 6. So we have 5 pi over 6 plus 2 pi n. We need to replace theta 2 with pi over 3 x is equal to 5 pi over 6 plus 2 pi n. Multiply both sides of the equation by 3 over pi to enable us to solve for x, where x is equal to 5 over 2 plus 6n, where n belongs to the set of integers. And that provides us with another value for x to solve this equation. So that answer, again, corresponds with A as a multiple choice answer. Let's look at another example. Determine all solutions in degree measure for the equation. Cosine of a half times x minus 90 degrees is equal to a negative √2 over 2. Notice this time that we can express our answer in degree measure. So the first thing we will do is replace 1/2 times x minus 90 with theta. So we have the cosine of theta is equal to a negative √2 over 2. And this is an equation that we are familiar with. Notice that cosine is negative. Cosine is negative in quadrants 2 and 3. So we can sketch a diagram of the unit circle to represent the given information, putting a terminal arm in quadrant 2 and another terminal arm in quadrant 3. The cosine is a negative √2 over 2, so the sine will be a positive √2 over 2, and the related reference angle in degree measure is equal to 45 degrees. In quadrant 3, we have a negative root 2 over 2 and a negative root 2 over 2 and the same related reference angle. So now in quadrant 2, the first angle theta is equal to 180 degrees minus 45 degrees plus 360 degrees times n. So the first value of theta would equal 135 degrees plus 360 n. We need to replace theta with 1/2 times x minus 90 in order to solve for x. So now what we'll do is we'll multiply both sides of the equation by 2. So you have 2 times 1/2 times x minus 90 equals 2 times 135 plus 360 n. The left side leaves us with x minus 90 degrees, and on the right side, 2 times 135 is 270 degrees plus 720 n. X is equal to 270 degrees plus 90 degrees plus 720 n. So one value of x is 360 degrees plus 720 n. This represents one set of solutions for this equation. Similarly, in quadrant 3, the second value for theta can be determined by taking 180 degrees and adding the related reference angle of 45 degrees. And to get back there again, we add or subtract multiples of 360. And in each of these cases, the value of n belongs to the set of integers. So then the second value of theta is equal to 225 degrees plus 360 degrees times n. Solving for x, we replace theta with 1/2 times x minus 90 will equal 225 plus 360 n. We will multiply both sides of the equation by 2 to help us solve for x. So we have x minus 90 degrees is equal to 450 degrees plus 720 degrees times n. Adding 90 to both sides of the equation, you have x equals 450 plus 90 plus 720 degrees times n. X is equal to 540 degrees plus 720 degrees times n, where n belongs to the set of integers. And this represents another set of solutions that satisfies this equation. And to conclude with the final example, we are asked to determine the general solution for 2 times the sine of x plus pi over 6 is equal to root 3. And we are asked to express our answers in radian measure. Let's first of all isolate the sine of the angle given by x plus pi over 6 is equal to root 3 over 2. So then we will let theta be equal to x plus pi over 6. So we can rewrite the equation as the sine of theta is equal to root 3 over 2, which is something that we are familiar with. Note that the sign is positive in quadrants 1 and 2. Drawing a diagram of the unit circle, we can put the terminal arm in quadrant 1 and another terminal arm in quadrant 2. If the sine is root 3 over 2, the cosine is equal to 1/2. And the related reference angle here is equal to 60 degrees, which is equal to pi over 3 radians. In quadrant 2, the cosine will equal a -1/2, and the sine is a positive √3/2 with the same related reference angle. So in quadrant 1, the first value for theta will equal pi/3 radians. We have to add multiples of 2 pi n, where n belongs to the set of integers. Now we will replace theta with x plus pi/6 is equal to pi/3 plus 2 pi n. We will have to subtract pi/6 from both sides of the equation. So x is equal to pi/3 minus pi/6 plus 2 pi n. Using a common denominator, we have 2 pi/6 minus 1 pi/6 plus 2 pi n, and one solution will be pi/6 plus 2 pi n, where n belongs to the set of integers. Similarly, in quadrant 2, we have the second value for theta can equal, that would be given by pi minus the related reference angle of pi/3, and we still have to add multiples of 2 pi n, where n belongs to the set of integers. So the second value of theta, pi is the same as 3 pi/3 minus pi/3. So we have 2 pi/3 plus 2 pi n. Replacing theta with x plus pi/6 equals 2 pi/3 plus 2 pi n. And now what we have to do is solve for x by subtracting pi/6 from both sides of our equation. Common denominator is 6, so we have 4 pi/6 minus pi/6 plus 2 pi n. So x is equal to 3 pi/6, which is the same as pi/2, plus 2 pi n, where n belongs to the set of integers. And this represents the general solution that satisfies this equation. So you can solve trigonometric equations algebraically and express your answer as a general solution, as we've done throughout those 5 examples. This concludes our review for Chapter 5. If you have any questions related to any of these presentations, please pose your questions in the question forum, and we will be happy to answer them for you. Thank you, and good luck as you continue with your review.